From the home to the factories, smart connected devices are an increasingly critical aspect of our everyday data experiences. Devices and appliances all around us are getting smarter. They increasingly contain logic, multiple sensors, connectivity, memory and storage, generating data as we go through our daily lives. The average US household now has a total of 25 connected devices across 14 different categories. That's up from 11 devices in 2019. The main reason that these devices are getting smarter is relatively simple. The intelligence of these devices makes them easier and more productive to work with. Adding additional functionality often allows these devices to take on more tasks, remember histories, and provide greater accessibility, and improve the quality of our lives. Of course, these advanced functions often require a rather significant amount of computing power, memory, storage, and connectivity. This also means that the resources required to provide the function may exceed what can really be hosted entirely in the device itself, for many reasons. Let me share just two examples to give you a sense of the scale and highlight how the devices and compute infrastructure at the edge and in the cloud complement each other. First, let's consider one of the most widely valuable capabilities, human-machine voice interaction. It would be nice to be able to interact with machines the same way we work with humans. But as it turns out, natural language processing is really difficult for machines. The largest AI models are using hundreds of billions and approaching trillions of parameters. And they require hundreds of terabytes of memory and petabytes of storage to train on supercomputing server clusters. The type of scale needed for training language models clearly requires a scale of computing power that's only available from a cloud-like infrastructure. However, certain inferencing use cases, such as more limited speech recognition capability or command sets, can be successfully achieved efficiently by using resources on the local device itself. But broader features or more compute-intensive algorithms can then be supported by having that device integrated with compute capabilities available at the intelligent edge and the cloud. Let's look at another example of this. Our automobiles. Continued advances in advanced driver assistance, in-vehicle information and entertainment, and the broader electrification of cars are all driving dramatic semiconductor growth in the automotive segment. Current generation vehicles have orders of magnitude higher chip content versus prior generations. And that growth is accelerating to make automotive one of the fastest growing markets for many segments of the industry, memory included. As we look ahead to increasingly autonomous vehicles, all the way to level 5 and full self-driving capabilities, the capacities of memory and storage needed to implement these safety-critical, intelligent systems grows by more than 100x.